Hello. How is your Friday going? It is 22nd of December and yeah, it looks like Christmas came early. So today I have got this in mail. Yeah, look at that. It's a box that says R-tape cutting error. Do not open with sharp instrument. Which I am totally gonna do. I'm gonna show it this knife. Let's see. I've been so nice. So nice this year so that I got this box as a present. So let's see what's inside. Just gonna open this here on off camera because I don't have a good bird's eye view that I could put, but yeah, let me just open this up from the sides. Can I get in? Yeah, like this, and then here in the middle. And what do we get? What do we get? Maybe I can put it. Let's do top. And yeah. Maybe I can put it in here. Can I make it fit? Oh yeah. Oh my god. Look at this. Look at this. I have this kind of thing. Oh, the glare is kind of huge. ZX Spectrum Next personal computer. Oh, look at that box. It's just gorgeous. It's just absolutely gorgeous. Let me get the styrofoam off so you can see. Sinclair TB, powered by TB Blue, it says. ZX Spectrum Next. Two megabytes. What's at the back? What's on the back? Maybe I should. Can I rotate this? Transform. Rotate 180 degrees. Let's see what's in the back. ZX Spectrum Next personal computer. The ZX Spectrum Next is the evolution of the original Sinclair 8-bit computer that kickstarted a generation of bedroom programmers whose games shaped the way we play to this day. It is fully compatible with the ZX Spectrum, including its younger siblings such as the 128 plus 2 and plus 3. You can even load your old tapes. Built from scratch with dedicated hardware, the ZX Spectrum Next boasts added features that make playing the original games a breeze, and opens the door for brand new titles taking advantage of its improvements, such as better audio, more colors, larger memory, and faster processor. Prepare to fall in love with a computer all again. Oh. CPU processor. Enhanced FPGA pace Z80 CPU running 3.5 MHz with additional toggle modes up to 28 MHz. Memory 2 megs of RAM on board. Graphics 640 by 256 pixel layered color display capable of 512 colors with hardware accelerated tile-up scrolling and sprites. Also supports Timex Sinclair screen modes. Like, why are we doing this on a Commodore when there's a ZX Spectrum Next, right? Right? No, of course, I'm just kidding. I'm just kidding. Yeah, I am not going to take this off the shrink wrap. Not in this video. We're gonna be doing everything in with our beloved C64. Of course, we're not gonna abandon this buddy. We're gonna keep going with developing this challenge to the end with the C64. We're so close, but yeah, this is gonna be a toy for the coming year, for sure. Okay, I'm just gonna put it back in the box. Back in the box, back into the styrofoams you go. You're not getting your prime time just yet. But yeah, that is a gorgeous thing waiting to be leveraged. Cool. Okay, back in the box you go. Ah, wow, that was something. That was something. But of course, the C64 all the way, 6502 CPU. Yeah. I'm sorry I'm teasing you, little buddy, but okay. We're gonna go with the C64 and yeah, back to regular programming. So today is 22nd of December. Yesterday's puzzle was quite the challenge. It took me a little bit to figure that one out, but yeah, in the event, eventually I did get this 2 stars, but and I did get to compute the result also on C64. So the Commodore has had 2 stars from yesterday's puzzle. It was quite the work to get that going, but in the end the solution was computationally quite light, so it took like a couple of minutes for the C64 to compute the solution, but I did have to develop that on the PC. But anyways, that's about yesterday. Now let's have a look at today's puzzle. So 22nd of December. And let's go to printing the message. Here we go. Okay, that was a journey. So you can see I had to switch the paper feed on the printer, and it looks like I didn't line it up perfectly. So you can see how this paper, let me get it out here. Up here. Let's get this out. So yeah, so the tractor feeder unit got slightly misaligned, so it started basically breaking off these edges. It's a little bit difficult to properly align that. I was kind of surprised that I was able to properly align it the first time, but yeah, now it didn't quite work, so I have to try that again. Okay, but still, we got the print even though it's a little bit off to the side. And now where's my pen? Okay, now my pen has traveled again. Okay, here it is. Here it is, and it's the day 22 sand slabs. Enough sand has fallen. It can finally filter water from Snow Island. Well, almost. The sand has been falling as large compacted bricks of sand, piling up to form an impressive stack here near the edge of Island. In order to make use of the sand to filter water, some of the bricks will need to be broken apart, nay, disintegrated, back into freely flowing sand. The sand is tall enough that you will have to be careful about choosing which bricks to disintegrate. If you disintegrate the wrong brick, a large portion of the stack could topple, which sounds pretty dangerous. The elves responsible for water filtering operations took a snapshot of the bricks while they were still falling. Your puzzle input, which should let you work out which bricks are safe to disintegrate. For example, okay, now we get to weird syntax. So there's like 1, 0, 1, and then there's this kind of character thing, which again I'm pretty sure like this is not an ASCII character, but this is something in Petsky. So there's some ASCII character here that doesn't have a counterpart in Petsky, so that's why this comes out wrong. So there's 1, 0, 1, and then 1, 1, 2, 1, delimited by something, and then looks like there's this other thing as well. Each line of text in the snapshot represents the position of a single brick at the time the snapshot was taken. The position is given as 2 XYZ coordinates, one for each end of the brick, separated by a tilde. Oh, that's a tilde. Okay. So it's a tilde symbol. Gotcha. Each brick is made up of a single straight line of cubes. And the elves were even careful to choose a time for the snapshot that had all of the free-falling bricks at integer positions above the ground. So the whole snapshot is aligned to a 3-dimensional cube grid. Alright. How nice of them. A line like 2, 2, 2, 2, 2, 2 means that both ends of the brick are at the same coordinate. In other words, the brick is a single cube. Line like 0, 0, 10, 1, 0, 10. Or 0, 0, 10, 0, 1, 10. Both represent bricks that are 2 cubes in volume, both oriented horizontally. The first brick extends in the X direction while the second brick extends in the Y direction. Okay, so in this case, this one differs in this code, so that's X coordinate. And this one differs in this one, that's a Y coordinate. So first brick extends in the X direction while the second brick extends in the Y direction. Both oriented horizontally, so Z must be up, because otherwise these wouldn't be horizontal. A line like 001, 0010 represents a 10 cube brick which is oriented vertically. Yeah, okay, so Z is vertical. One end of the brick is the cube located at 001, while the other end of the brick is located directly above it at 0010. Alright. The ground is at Z equals 0 and is perfectly flat. The lowest Z value a brick can have is therefore 1. Okay, so it consumes the Z equals 0 layer. So 551 and 561 and 021, 205 are both resting on the ground. But 332, 333 was above the ground at the time of the snapshot. Okay. Because the snapshot was taken while the bricks were still falling, some bricks will still be in the air. You'll need to start by figuring out where they will end up. Okay, so I need to drop them. Bricks are magically stabilized. So they never rotate, even in weird situations like where a long horizontal brick is only supported on one end. Two bricks can occupy the same position, so a fallen brick will come to rest upon the first other brick it encounters. Here's the same example again, this time with each brick given a letter, so it can be marked in diagram. Okay, so A, B, C, D, E, F, G. At the time of the snapshot from the side of the x-axis, from the side so the x-axis goes left to right, these bricks can be arranged like this. What? Okay, 0 is ground. Z, okay, so this one goes up. X, 0, 1, 2. Okay, so now I understand. So X left to right, 0, bottom to top. And there's the bricks. Rotating the perspective 90 degrees. So the y-axis now goes left to right. The same bricks are arranged like this. Okay. Once all of the bricks fall downward as far as they can go, the stack looks like this, where question mark means bricks are hidden behind other bricks at that location. Okay. This looks like a Jenga board. Again from the side, yeah. Now that all of the bricks are settled, it becomes easier to tell which bricks are supporting which other bricks. Brick A is the only brick supporting bricks B and C. Brick B is the one of two bricks supporting brick D and E. Brick C is the other. Okay, yeah. The first task is to figure out which bricks are safe to disintegrate. A brick can be safely disintegrated if, after removing it, no other bricks would fall further directly downward. Don't actually disintegrate any bricks, just determine what would happen if, for each brick, only that brick were disintegrated. Bricks can be disintegrated even if they are completely surrounded by other bricks. You can squeeze between bricks if you need to. In this example, the bricks can be disintegrated as follows. Brick A cannot be disintegrated safely. If it were disintegrated, bricks B and C would both fall. Brick B can be disintegrated. The bricks above it, D and E, would still be supported by brick C. brick C can be disintegrated. The bricks above it, D and E, would still be supported by brick B. Okay. So in this example, 5 bricks can be safely disintegrated. Figure out how the blocks will settle based on the snapshot. How much they settle? Consider disintegrating a single brick. How many bricks could be safely chosen as the one to get disintegrated? Alright, so we need to drop these bricks. And then calculate which ones are the supports. Okay, let's get some puzzle input. Oh, what is that? No. Okay, so puzzle input here. Nine 2023 example 22 txt. And then the puzzle input into device 9 23 input 23. I'm thinking that this is this feels like this problem should be solvable by like in linear one pass, it feels like. Let's see if that is the case. Include libc.h int main close or f equals f open 2023.example 22 txt up. Read. Okay, so there's that. And then now I'm gonna use scanf. So I have integers of x, y, and z. While fscanf from file %d, then there's that weird character %c, and then again %d. X 0. So I can just do x, y, z, dummy, x plus 1, y plus 1, z plus 1. greater than 0. Yeah. Print f x 0 y 0 z 0 x1 x1 y1 z1. No, not y1 z1. Yeah, and then close the file. Okay, set the device 9, 2022 ACDP. Is this gonna work? Yeah, it does. Okay. Let's run through int n 0 plus n. Let's look through the input. Oh, there are huge numbers. Okay, I need to also calculate the maximum extent. So oh, but the x and y values are from 0 to 9. X and y values are from 0 to 9, and then z values can be really huge. Yeah, that's right. Okay, so we need the 10 by 10. Oh, there's a lot of those. Going at 500 now. Jeez. And wait, these don't seem to be ordered like in the falling order even. Because there's like here 833, 835. So it's like the 859th brick is so I cannot even like make these fall in online order. That's super annoying. Because otherwise I could just process this line by line, make them fall, track like the XY landscape and all that stuff. But now I have to first read all of these in memory. How many of them are there? How many of these are there? There's like several hundreds. 100. Okay, so 1,455 bricks. And I need to sort them. So what is it? I need 1 byte for X, 1 byte for Y, and then 2 bytes for Z. So that's 4 bytes. So that's 6,000 bytes. But yeah, that will fortunately fit. Okay, yeah, let's sort these. Let's sort these. So struct. Oh no, that's more bytes than 4 bytes. That's 8 bytes per brick. Struct brick. U8 X2 Y2 and U16 Z2. Bricks 1500. So that's 12,000 bytes. Still okay. Bricks n plus plus equals this. No. I wonder what this issue is. Do I need to... Yeah, I need to cast explicitly. Oh no, not for this. Oh no, apparently I do. Oh, not U8, the U16. Non-constant exception cannot be something. So I... Oh, no, that's because I did it. This has to be X0, X1, Y0, Y1, Z0, Z1. But like, what the heck? Okay. That was odd. So let's do this. And then I'm gonna get this one for int I equals 0, I is smaller than n plus plus I. Well, let's name this brick so I can do brick b equals bricks. And then I can do what it doesn't look like. What am I missing? Okay, what am I missing? Oh, I'm missing nothing. I had a code synchronization issue. Okay. And then I have the quick start algorithm from that one day. So if I implement a bool operator less than brick or return z0 smaller than r v0. Then I can do q sort bricks n. And now I should have sorted bricks when I print. Let's see if that is the case. Sorted by lowest z, and that is actually the case. So I have now sorted bricks. Do I wanna, let's, no, it's gonna take ages. It's gonna take ages. I'm just gonna run this example first. So, and now I can drop them. So I can. So how do I do this? So when I fall a brick, I have to look at which brick is underneath it and mark that brick as supporting. But if instead that brick falls on 2 or more things, then not. Okay, so I can here put in bool fixed. So I cannot remove this, and then I do int map 100. But then I need a dummy value. I need a... Let me put in n equals 1, so n equals 0. Like the first brick is then the dummy ground. So initially the map is all zeros. I'm using these integers refer to this array. So initially all map indices refer to the 0th brick, which bricks 0 fixed equals 2, which cannot be removed. I don't know if I need this, but yeah, so there's that. And now when I look at brick, I need to figure out which way it's No, actually what I do is int find unique support for brick B. For int y equals brick y0, y is smaller than brick y1 plus y. For int x equals brick x0, x0, x is smaller equal to bricks x1 plus x. So I'm looping over the surface area of the brick. And then I need to know what is the z value? What is the z value that it's gonna hit on the map? So brick support, like the potential support for this brick is bricks y times 10 plus x. Might change this later to 16, but 10 is 8 plus 2, so it's not that much of extra arithmetic. Int highest or high z equals 0. So I'm looking for the tallest brick, the tallest unique brick under this XY grid. If S, let's do -1. If S Z2 is greater than high Z, high Z equals SZ2. Unique equals true. Else if S Z2 equals high Z, unique equals false. So unique false. I guess this can be anything. Oh! Thank you, compiler. Yeah, this feels good. I loop over all the elements or all the squares around this brick. Find the tallest brick under this brick. Because if this brick is gonna fall on just one unique thing, then that unique thing cannot be removed. Like, if a brick has two supports, then either one of them could be removed. But if there's just one brick that is gonna one unique support for this, then that support brick is critical and it cannot be removed. Yeah, so if unique, and I guess I need to put in this okay, I think this has become a full-on drop function. Let's do boolean drop. Let's do void int support. Well, I guess I'm gonna do just brick equals 0. And actually I don't need this. I can do unique support equals 0. And then unique support equals S. And here unique support equals 0. If unique support let's deliver both, but whatever. Unique support and unique support fixed fixed equals true plus num fixed. So I'm gonna have this global count of num fixed. Yeah, that feels good. So, oh, and then I need to actually update the z value. So now that I've dropped the high z value, so yeah, so now I need to do brick z. So I have the height of the block equals brick z1 plus 1 minus brick z0. 0 equals high z plus 1, brick z1 equals brick z0 plus height minus 1, but then I just don't do this at all. So this is just high z plus 1 plus h. Right? Yeah. Yeah, that looks about right. Oh, then I need to update the map as well. Oh, yeah, now I need to update the map. Map y times 10 plus x equals Oh. Equals index. So I'm gonna do here drop ID I plus 1, because I'm not gonna drop the ground. Then so I'm first gonna drop all bricks, and then I'm gonna do a debug print to figure out fix it or isn't S be fixed, then fixed, otherwise nothing. And then here, what was the question? How many bricks could be safely chosen to be integrated? So that is, let's do a fix, n is n minus 1, because I have the ground here, so I need to subtract that. And, or let me just print the n. And then fixed equals %p num up, number of fixed bricks. And then finally disintegrate %p is, this is how many bricks I have, minus num fixed. Okay, let's see what happens with this one. Everything can be disintegrated. And everything is at z equals 0. Well, that's unexpected. Oh, is that because I'm mixing signed unsigned? Yeah, that was a problem. So brick A cannot be disintegrated. So A is 1, and I get it fixed. Brick B can be disintegrated. Oh, actually, oh, I have a bug here, and S is not unique, because I might be the top brick might be resting on that support brick in multiple positions. So that's one bug. But that didn't change anything. Oh, actually, 5 bricks can be safely disintegrated. I do get the right number, but which ones are fixed? Brick A, which is 101122, yeah. And brick F cannot be disintegrated. What is brick F? 0121. I don't have. Where is 0? That's 6. Okay, so I get the right number by chance, but I'm not getting the right bricks. Okay, what is wrong with my logic? Let me try to draw this from above. So according to my things, I'm getting 1 0 1 1, or actually x1. So this is like 3 by 3. X equals 1 0 to 1 2. Which is here, and z equals to, but that's all. Okay, so that must be wrong somehow. Yeah, like what the heck? Okay, my height computation must be wrong. So this is the height of this brick. One falls. The first brick falls to z equals 2. That's just not possible. Why is that possible? Report. Oh, Oh, map. Jeez. Did I do the same? Yeah, I was just looking at the end. Okay, now I understand. Yeah. So let's now see what this prints. So 2 bricks can be disintegrated. 1, 0, 1, 2. Or 2 bricks cannot, yeah, 2 bricks cannot be 1, 0, 1, 2, and then 0, 1, 2, 1. 0, 1, 2, 1. Yeah, okay, so now, now I have the right answer for the example. So let's give it a go. Oh, hi Smab, okay, finally caught a stream again. Sorry, didn't notice you here. Wasn't looking at the chat for a moment here. Was too deep into working on this thing. But yeah, now I think I might be ready to run the first part to see if this works. Yeah, let's just run it like this. Only just got, okay, yeah. Yeah, I find that when I get really deep into looking into the code, I don't see if somebody types something. Okay, feeling a little bit confident about this part. Let's see what happens if I get this right. So there's about 1500 bricks. How many of them can be disintegrated? How many of them can be disintegrated? Once the disk loads, I think this should be a fairly quick computation because it's gonna do the sort. Okay, so that's gonna take a little bit of time, but after that, it's a linear walk. But yeah, there's a lot of input data in this one, so this one takes a little time. Okay. And then it computes. Cool, and then it gets a lot of fixed blocks and some blocks that can be disintegrated. That looks fairly decent as far as data goes. Many are fixed, but also many are disintegratable, so feels plausible. The Z numbers are growing, they also look plausible. Yeah, Z values grow. They sometimes sometimes shrink, but I think that's to be expected because they are like these blocks that are different coordinates. And then the very last blocks that come out, they should definitely be disintegratable because they are on top of everything else. $505 disintegratable. The question was how many blocks could be safely chosen to be disintegrated. Okay. Okay, so 1 hour 8 minutes in, and I'm going for the first answer. First try. Let's see what happens. 22. Answer 505. Is that the right answer? Is that the right answer? It is the right answer. First try. First try. Only a minor indexing bug. And I got the solution. Yay, I'm happy. Okay. Okay, what's gonna be in part 2? Now, it's a star. It's a star for sure, yeah. Now, I'm not gonna lie. If if the second part is gonna be an infinitely cycling input of bricks that we are following the same sequence of input numbers a billion times, then I'm gonna be a little bit sad. But we'll see what happens. We'll see what happens. Yeah, you are just at the right time. Okay, you arrived at the right time to see me try to adjust this printing paper into this Commodore printer. So I need to get this tractor feeding unit, get this paper in just right so it doesn't. I need to release this clip, open these, and then get these things in here like this so that they are just right. Because otherwise this thing is gonna start to crumble. So let's hope that works. No idea. And then I need to paint this. Okay, let's give this a print. Hey. That was very little printing, which is actually kind of scary because sometimes just with very small changes the result is gonna be okay, just one page. I think you'll like this part. Okay, well, let's see what's gonna happen. Part 2. This integrating bricks one at a time isn't going to be fast enough. While it might sound dangerous, what you really need is a chain reaction. You'll need to figure out the best brick to disintegrate. For each brick, determine how many other bricks would fall if that brick were disintegrated. Using the same example as above, disintegrating brick A would cause all 6 other bricks to fall. Disintegrating brick F would cause only one other brick, G, to fall. Disintegrating any other brick would cause no other bricks to fall. So in this example, the sum of the number of other bricks that would fall as a result of disintegrating each brick is 7. Each brick, determine how many other bricks would fall if that brick were disintegrated. What is the sum of the number of other bricks that would fall? Okay. Well, it wasn't an infinitely cycling thing. I'm happy about that. I mean, there has been so many of those that you kind of like you get triggered or like you're already on the lookout for that kind of happening. I still have a micro peripherals MP165 printer. Oh, interesting. Is that's a an old dot matrix as well, or also the same kind of thing? Oh, and it cascades, because this little brick 8 would cause all 6 other bricks to fall. Now I understand. Not just like the immediate thing. Probably a similar vintage, yeah. Yeah, that's this is old but reliable, it looks like. Brick all A would cause all 6 other bricks to fall. Brick F would cause only 1 other brick G to fall. So I feel like okay, so I've identified the fixed bricks. I've identified the fixed bricks. I had it with my computer's links, I think. Yeah. So if I run on this example again, there's those 2 bricks that are fixed. So when I have a fixed brick, let me actually hand draw this graph. So we have brick A. Oh, how do I do this? Oh, not like that. Not like that. Okay. Okay. Camera operator accident. So if I have A is supporting bricks B and C. B is the one of 2 bricks supporting D and E, and so does C. And D support. Okay, now I ran out of paper. Why did I have to draw so high? D supports brick F. E also supports F. And then G. Okay, so I have A. I have A, B, C, D, E, F, and G. So that's my graph in this case. Like this. So I couldn't remove So this one is fixed, and this one is fixed. This is how it goes. So I'm clearly doing a graph search here. The graph search is, so the reason why A topples everything in here is that if I start here, like if I start on any of these nodes and start going backwards on these edges, they will all lead to A. Instead of leading to so actually have here the zero, the ground brick. So when I'm doing a graph search backwards from these edges, I have already I have these booleans that mark fixed bricks. Hold on, but is that true necessarily? Because if there was like a hypothetical thing, if there was a hypothetical another thing like H here that supported this one. Then the reason why this doesn't topple is because if I do a graph search backwards from here, I can only reach, or I will reach 2 fixed bricks. So is that my naive solution? My naive solution is go through every brick. For each brick, do a search like backwards from these edges. And if, like, do like a flood fill search. And if that flood fill search, that frontier dies into a single, or like sinks into a single fixed thing, then that thing gets all the score, all the bricks. Oh no, then that thing gets +1 from this thing. So that's a naive solution, but then there's also this transitivity that okay, no. The naive solution is go through every brick and then find the fixed bricks that support it. So in this case, G finds F. Then mark a +1 because if you topple this one, that's a +1. Then for D, you don't give a +1. To these. You give a +1 finally for this. So when you get but then for F needs to give not just +1 but the amount of stuff that lies on top of it today. So that I think would be a naive solution. But I don't want to do a graph search starting from every node and then every node and then if you know, like that would be like super quadratic algorithm to go like graph search from every node onwards. What I want to do is do a single graph search. So what I was doing incrementally is, I started from the ground, I added a brick. That brick was marked to not support anything. Then I added another brick. If that has a unique support, then that gets fixed. Then I add another brick. It doesn't have unique support. It doesn't have unique support. This one doesn't have unique support. This one has unique support. I'm thinking like, can I just accumulate counters? Instead of doing any kind of graph search, could I do when I do this unique support, you get a +1 because you're gonna topple this over. Then this one comes along, oh, it's resting on this +1. Then this one comes over. In my search, currently I look at, oh, there's no unique support. But then I do need to transitively propagate, and I do need to do the graph search. But I wouldn't want to do it immediately when I plant down D to go like, oh, I have 2 parents, so let me search where I'm gonna propagate. No, I'd rather build up the whole graph and then start at the top and start propagating. So I start from G, I go does this brick have a unique support? Yeah, it does. +1 to this. Does this brick have unique support? No, it doesn't. No, it doesn't, so it has multiple parents that it's resting on. Do I then propagate? So So I start here. I have a count. I'm carrying a counter of 1. I go to parent. Do you have Unix support? Yes. You get my counter. Then I increment the counter. Oh, there's now 2. Then I look at the parents. No Unix support. Counter is at 3. My search frontier is at 4. Accumulating into this. Oh, but this does kind of, this does kind of get more complex, because for these then I could think I cannot think in one search frontier, because then these two, they might have different supports. Or like different links in my search frontier could have different support. So, So what this example scenario doesn't show is exactly the presence of this kind of thing. That would be a support. And the reason why this one gets all these scores, because you don't have a path from here to here without going in between of A. Everybody has to go through A to get to the ground. So that's why A supports everything. But if there was a H also lying on ground that was supporting B, then if you search a path from G to ground, you have multiple nodes. You have multiple nodes to go through here. So it's always about this kind of finding a choke point. If you start a search at any point, and whenever that search shrinks to a single point, then that gets the count. But I'm struggling to see how I can do this without doing a graph search for every node. Without doing a graph search from every node. Hmm. Do I do a float fill? I start from... So I could have here an edge. If I had here an edge of something, or like a leaf node, or like a sink, then this would become this kind of thing. Yeah, I'm okay. I'm feeling here. I've jumped over to Captain Coder as well. Okay, good to see that that they're also online. Yeah, curious to see how he handles this. Okay, so now I think what my approach is gonna be, or do I? So I have these leaf nodes, like nodes that don't support anything, or like that don't have. So this one, this S, let's say this is S and G. These are leaf nodes. So I take an arbitrary leaf node, and then I start a flood fill, like a boundary search through this graph backwards through these edges. And this search stops. It can only traverse these non-fixed nodes. It traverses up until it finds these fixed nodes. So it traverses backwards these edges until it finds these fixed nodes. And then it looks at the fixed nodes that it finds, and then it figures out like, did I end up in just a single fixed node, like in this case, or did I... So if this was here, did I end up in two fixed nodes, like this? But wait, if I do this is then not a fixed node. So if I start a search from a leaf, Then if I run into a single of these, then I can count all of those, accumulate them into this one. And then I can continue. Do I need to manage this graph? I guess I do. So yeah, I think that's my algorithm. Take a leaf node, walk the graph backwards until you find all the fixed nodes. Can you ever run into two fixed nodes? Yes, you can, because if you start here, no. If you started here, you would run into this and then into this. Which is kind of interesting. Because that means that these things have also z values, which actually helps me find a traversal order, because these these are the z values. So if I start from a leaf, and I go backwards and I find a unique supporting node, then I can basically replace that graph with the idea that whatever flowed into this unique supporting node could be replaced just by that node and then whatever. If a node is a fixed node, then that means that there exists some other node in the graph that has the only path to ground is through that node. That's what fixed means. There exists some other node on the graph that its only path to reach the ground is to go through that fixed node. And that's why that fixed node should get that point from this node. That's removing that node would topple this other node over. So does this reduce to some of those max flow, min cut, or max cut problems? Not flow, but cut problems. Basically, if I redraw this, I have ground, then oh no, I wanted to redraw, so A goes to ground through here, C, B, D, E, and F. And now in this graph, the question is to score for any node in the graph. The score is how many other nodes have their path to ground being unique through A. Yeah, so if I have ground, and if I have A, B, C, D, E, if I have like this, then these are fixed nodes, because C and E have the only path to ground through them, but D has a choice, so it so yeah, so it should work though. If I start from a leaf, and I go through and I find all the paths to all the how many fixed nodes this path can reach. If that's more than one, that whole subgraph is not going to accumulate any points. hold on, do I need to even do any graph stuff? Maybe I do, maybe I do. Yeah, so my thinking is pick a leaf, find all the fixed nodes it can reach. If it can reach only one, then that whole subgraph that it walked through, that size accumulates to that fixed node. And the same here for E. And then when I have accumulated that thing, I can basically not look into those things again. Likewise for these. And when I've done that, then I'm going to, I have to start basically walking the whole. So okay, now I think I know how to solve this with just one graph traversal. Or, I mean, multiple graph traversals, but they never look at any edge more than once. Yeah. So the algorithm is repeatedly pick a leaf node that has 0 in edges. Then find all the fixed nodes it can reach. If it reaches more than one, then those can be discarded. Like this D. It doesn't accumulate to any score. Then that can be discarded, that whole subgraph. So then pick another one with 0 degrees. And when you discard a node, then you have to reduce the in degrees for the nodes that it points to. So basically we remove that from the graph. So you pick a leaf, no in degrees. Do the search, you find a unique fixed node, you add the size of that subtree in there. Then you remove the in degrees. Then pick another leaf. Find all the fixed nodes it reaches. If it reaches multiple, don't accumulate. And then you cut that from the tree. Then find another node with no in leaves. Then find all the fixed support. You accumulate and cut. Then find another, now we're at A and B. Find all the ways that it can reach 0 to fixed nodes. In this case, it goes to ground. So we accumulate ground basically, but it doesn't mean anything. So yeah, so I think that's a solution that uses graph traversal. And do I absolutely need to use graph traversal? Yes, I do, because in this example, this A this A get, like if I don't have this, none of this stuff, A is gonna get, or here's the original one, A is gonna get the score of all of these. And there's the G was on top of here. So I cannot calculate this score by... Yeah, I cannot calculate this score just by... I need to do it from top, because if I had this one, like ground, A, like just this kind of linear tower, C, D, E. So a long linear tower of blocks. A, of course, should get score of all of those. B should get the score of all of them above, C above, D above. So if I wanted to do this incrementally immediately after I have placed a block, then that would mean that any step here along the way, like E, I would have to plus one, plus one, plus one, plus one. Then I get to F, plus one, plus one, plus one, plus one, plus G, plus one, and so forth. So that would be a quadratic algorithm if I do that. So I do need to do this kind of backwards in order to get that linear runtime. Yeah, I'm pretty sure that this is now the way to approach this. I am at 1 hour and 55 minutes mark. Do I try to do this on the C64? That's what I'm thinking. That's what I'm thinking. Let's see. 2022 B. I do want to break off for lunch pretty soon. So what would my data structure look like? For all bricks, I would want to store for them a vector of indices of like on top of. So I would have for each brick, I would be maintaining which other bricks it is on top. And then I would have to have a traversal. I would have to have another Boolean visited for the second part graph search. And then my leaf, from leaf to first, that would be, that could be a Z order from top to bottom. And in B part, I don't need to have the number of fixed nodes. I don't need to do this anymore. So I would have this. And I would first drop all the bricks. And then in reverse order, I would do int I equals n minus 1, y greater than 0. I. and I would do a search, graph search on bricks. Void search brick B. And then if this one has already been visited, return brick visited. And then I also need to do int num support. I have to store how many bricks this brick supports, and that's the score that I'm calculating. And here I have to build this on top of if s oh no if b on top of back is not maybe I'll instead have brick pointers in here. They're the same size as integers anyway, so that should work. If be on on top, if be on top empty or be on top size equals 0 or on top back is not S. Be on top push S. So now I'm building this graph to find for each brick what are all the bricks that brick is on top of. Oh, no, this is not. Of course, if is equal to high Z and no, if that supporting bricks Z1 equals high Z. And okay, now I should have the graph. Okay, so now I know for each brick which other bricks it's on top of. Yeah. Oh wait, does this become a simple? No, it doesn't. No, it doesn't. It's not a simple accumulation because of this very example. D is on top of A and B, so I don't. Yeah. Okay. Actually. Hold on, let's go back to my example. I thought I had this, but do I have it? So if I have ground, and let me simplify this example in a way that I don't have C. I have A, and I have B, and I have D resting on A and B, and then I have E resting on B. So this is not a fixed node because I can remove this. D is also here. But B is a fixed node. And ground is. But these always have Z values, so I can stop my search. I thought I had it, but I don't. Maybe I don't. Because I could have also this. I could have A that is a tall block, and then B, and then C, and then D. So here, B is fixed. Because C is on top. So my algorithm thinking that I would do this search and I would only need to look at each node once doesn't quite work. Because here I would search D, C, A, and that's fixed ground, and that's fixed B. And then I wouldn't need to consider. But of course C does reside on top of B. Ooh, okay. Okay, so that's not quite working. I do have to think about this some more. But yeah, I do. This is a good spot, so I've been out like 2 hours. I do need to now get lunch. Interesting challenge for sure. And I think the Z values might be something. I don't probably want to treat this just as an abstract graph, but I also want to treat this as the Z values that these blocks have. Because I do want to do the search in a way that, do I run into a single block with a single at some Z value that supports them, but yeah. So quadratic solution, a naive quadratic solution, do a graph search from every node would work, but that's not the nice solution. So I'll have to think about this some more. Okay, but anyways, this is everything for today. So I'm gonna head out for lunch. Take care, internet, and I will catch you. Actually, I will not catch you because this is actually the last one that I am able to stream now. So I'm heading out to Christmas holidays. So tomorrow, 24th and 25th. So the last 3 puzzles I am going to do then later at some time. So I won't be able to do those online. So that's an unfortunate thing, but yeah, those will be after the Christmas days. So anyways, take care, internet, and I will see you then. Maybe I'll stream them after, but maybe not, depending on how my schedule looks like. But anyways, take care and have a really nice Christmas and happy holidays and a great new year, and yeah, take care and bye.